Have you ever looked up at the night sky? It seems so calm and peaceful up there. Millions of tiny lights twinkle against a dark, silent background. But don't let that quiet appearance fool you. The universe is a place of incredible violence and power. It's a cosmic theater where amazing events happen all the time. We just can't see most of them with our own eyes. These events involve forces so strong they are hard to even imagine. They are bigger and more dramatic than anything we could ever experience here on Earth. One of the most spectacular shows in the cosmos happens when two giants meet. A star, a blazing ball of hot gas, gets too close to a black hole, a mysterious region of pure gravity. Let's get to know our two main characters in this cosmic drama. First, we have the star. Stars are the building blocks of galaxies. They are huge, glowing spheres of plasma. Think of our own sun. It's a star. It provides the light and heat that make life on Earth possible. Stars are born from vast clouds of gas and dust. They spend most of their lives fusing hydrogen atoms into helium in their cores. This process, called nuclear fusion, releases a tremendous amount of energy. This energy pushes outwards, fighting against the star's own immense gravity, which is trying to crush it. This delicate balance keeps a star stable and shining for billions of years. On the other side, we have the black hole. If a star is a beacon of light, a black hole is a vortex of darkness. It is the complete opposite. A black hole is a region in space-time where gravity is so incredibly strong that nothing, not even light, can escape. That's why they are black. Imagine our unsuspecting star wandering through the cosmos. It's on a long, looping orbit around the center of its galaxy. This is a common path for many stars, but at the heart of most large galaxies, including our own Milky Way, lurks a monster, a supermassive black hole. These are the biggest black holes of all, with masses millions or even billions of times greater than our sun. For most of its life, the star keeps a safe distance. Its orbit is stable. But cosmic journeys are not always predictable. A nudge from another star or a close encounter with a dense star cluster can change its path ever so slightly. This tiny change in trajectory can have catastrophic consequences. It can send the star on a new path, one that takes it dangerously close to the supermassive black hole. This is the beginning of the end. As the star gets closer, the black hole's gravitational influence grows stronger and stronger. It's not just a gentle pull anymore. It's a powerful, inescapable force that begins to dominate the star's own gravity. The key to what happens next is something called a tidal force. As the star approaches the black hole, the gravitational pull on the side of the star closer to the black hole is immensely stronger than the pull on the far side. This tremendous difference in force starts to stretch the star. The star begins to lose its spherical shape. It gets distorted, elongating into an egg or teardrop shape, pointing towards the black hole. The star's own gravity is desperately trying to hold it together, but it's a losing battle. The tidal forces from the black hole are just too powerful. The star is being pulled apart from the outside in. As the star crosses the critical threshold of the tidal radius, the stretching force becomes catastrophic. The star is now being pulled and elongated with incredible violence. This process has a wonderfully descriptive name: spaghettification. Our star is being turned into a cosmic noodle. It is being stretched longer and squeezed thinner by the relentless gravity of the black hole. The gas on the star's surface is the first to be lost, forming a leading tail of hot gas. Even as it is being torn asunder, the star does not go quietly. The immense forces at play create a scene of unimaginable chaos and energy release. The temperature of the gas soars to millions of degrees Celsius. Not all of the star's material is doomed to fall into the black hole. As the star is unraveled, roughly half of its mass is captured by the black hole, while the other half is flung away into interstellar space at incredible speeds. Once the star has been completely spaghettified, it ceases to exist as a coherent object. What remains is a long, thin, and incredibly hot stream of gas. This stellar stream is a river of what was once a star, now flowing through space. The stream of gas wraps around the black hole, colliding with its own tail on its first pass. This collision creates powerful shock waves and further heats the gas, causing it to glow even more brightly in X-rays. Over the course of weeks and months, this swirling stream of stellar debris settles into a more organized structure. It forms what astronomers call an accretion disk, a hot, rapidly spinning pancake of gas that orbits the black hole. The friction between particles in the disk generates immense heat, making the disk glow brilliantly across the spectrum. It is this glowing accretion disk, formed from the fresh remains of a dead star, that can outshine all the billions of other stars in its host galaxy combined. The dramatic shredding of a star by a black hole is not just a theoretical idea, it is a real phenomenon that astronomers have now witnessed many times. We call these events tidal disruption events, or TDEs for short. To catch one, astronomers have to cast a very wide net. They use robotic telescopes that scan large portions of the night sky every single night, looking for things that suddenly get brighter where nothing was bright before. When one of these automated surveys detects a new, bright point of light in the center of a distant galaxy, scientists must use other telescopes to get a closer look. They spread the light out into a spectrum like a rainbow, which has a unique chemical fingerprint. The light curve, a graph of the flare's brightness over time, follows a predictable pattern. It rises sharply as the star is torn apart, and the accretion disk forms, then decays slowly as the stellar material is gradually consumed by the black hole. So why do we get so excited about watching a star get brutally torn to pieces? These cataclysmic events are an incredible scientific gift. They give us a rare opportunity to study supermassive black holes that lurk silently in the dark at the center of most galaxies. A TDE provides us with a completely new and independent way to weigh a black hole. The physics of the event itself depends directly on the black hole's mass. By studying the light from a TDE, we can measure the fundamental properties of the black hole that caused it. Furthermore, these events allow us to test Albert Einstein's theory of general relativity under the most extreme conditions imaginable. A TDE is a real-world experiment that puts these predictions to the ultimate test. We can watch how matter orbits just outside the event horizon and see if it behaves the way relativity says it should. So far, Einstein's theory has passed every test with flying colors. One of the most fundamental questions we can ask about a supermassive black hole is simple. How much does it weigh? This technique allows us to measure black hole masses in galaxies that were previously inaccessible, helping us conduct a census of black holes across the universe. We want to know how many black holes of different sizes exist. Each TDE we find adds another data point to our galactic census, helping us build a more complete picture of the cosmic population of these monsters. Beyond teaching us about black holes themselves, tidal disruption events offer a unique window into the centers of galaxies. They help us piece together the grand story of how galaxies and their central black holes grow up together. The material that is flung out from a TDE plays a role in the life of the galaxy. They seed the interstellar medium with elements that were cooked inside the star, which can eventually be used to form new stars and planets. The study of what black holes do to stars is a field that is still in its infancy, and the future is incredibly bright. We are entering a golden age of observational astronomy. A new generation of powerful telescopes will revolutionize our view of the transient universe. Perhaps the most exciting frontier lies in gravitational wave astronomy. Future space-based observatories will be designed to detect low-frequency gravitational waves from events involving supermassive black holes, giving us a direct line to physics at the event horizon. The violent dance between a star and a black hole is more than just a curious cosmic spectacle. It is a fundamental process that shapes galaxies and reveals the deepest laws of nature. As we continue to watch these distant flares ignite and fade, we are participating in one of science's grandest adventures. So the next time you gaze up at the tranquil night sky, remember the hidden drama unfolding in the deep cosmos. The story of a star meeting a black hole is a story of destruction, yes, but it is also a story of discovery, revealing the magnificent and violent beauty of our universe, one shredded star at a time.